Tonight, we're going to take a journey to the edge of everything you can see, everything you can imagine, and then one step further, into the territory where the universe itself quietly closes the door. Somewhere out there, right now, there is a star so far away that its light has been travelling toward you for longer than the Earth has existed. A star so remote that by the time any signal from it reached your eyes, entire civilizations had risen, collapsed, and been forgotten by time. And here is the part that most people never stop to consider. You will never reach it. Not because the distance is too great, not because our rockets are too slow, not because we lack the will or the courage or the technology, but because the universe has built something into its very architecture, a rule, quiet and absolute, that makes certain destinations permanently, cosmically, and forever out of reach. There is a number that cosmologists speak about in hushed, almost reluctant tones: 46.5 billion light-years. That is the radius of the observable universe, the sphere of existence you can, in theory, detect from where you're standing right now on this small, spinning world. It sounds like a boundary, like a wall. But the terrifying truth is that it is not a wall at all. It is a horizon, and like every horizon you have ever walked toward in your life, it moves away from you as you approach. Only this horizon does not just move, it accelerates. The farthest stars and galaxies are not simply sitting at a distance, waiting patiently for you to arrive. They are rushing away from you at speeds that no engine, no ambition, no force in the known universe can overcome. Step outside on a clear night and look up. Every point of light you see is a sun, many of them larger, older, and stranger than our own. Some of those lights left their source before your ancestors walked upright on this planet. Some of them were already old before the first fish pulled itself onto dry land. The star you're looking at right now may no longer exist. What you're seeing is not a star. It is a memory, a ghost of fire crossing an unimaginable void, arriving at your eye after a journey so long that the universe itself has changed shape around it. And somewhere at the absolute limit of that darkness, past the last galaxy, past the last filament of cosmic structure, there are stars so far away that nothing will ever connect us to them again. This is not a story about distance. Distance is something you can solve with time and patience and speed. This is a story about the nature of reality itself, about a universe that is, at this very moment, quietly and relentlessly tearing itself apart, expanding faster and faster into a silence so vast it has no name. It is a story about the loneliness of galaxies, the death of horizons, and what it means to be a conscious creature in a cosmos that is, in the most literal sense possible, always moving away from you. By the end of tonight, you are going to understand exactly why the farthest star will always stay out of reach, and why that truth, as terrifying as it is, might be the most beautiful thing the universe has ever shown us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about the last time you stood outside at night and looked up at the sky. Maybe it was in a city where the stars were faint and few, drowned out by the orange glow of streetlights. Maybe it was somewhere quieter, a field, a mountain, a beach far from any town, where the darkness was real and the sky opened up above you like something alive. Either way, there was a moment, a brief, wordless moment where the scale of what you were looking at pressed down on you and something in your chest shifted. That feeling is real. That instinct is ancient, and tonight we are going to follow it all the way to the edge of the universe. Human beings have been looking up at the night sky for as long as we have existed. For most of that time, we had no real idea what we were seeing. The stars were gods, or spirits, or lanterns hung in a dome above a flat earth. They were patterns to navigate by, omens to interpret, fires lit by distant and unknowable forces. We gave them names. We wove them into stories. We built our calendars and our religions and our sense of direction around them. The sky was the original mystery, vast, permanent, and impossible to touch. In all the tens of thousands of years that humans have been alive and aware and looking upward, the stars have always been exactly that. Something you could see, but never reach. Then science arrived, and for a while, it felt like the mystery was being solved. We learned that the stars were suns, other suns like our own, burning through nuclear fusion at temperatures of millions of degrees, fusing hydrogen into helium and releasing energy on a scale that dwarfs anything we can produce. We learned that some of them were larger than our entire inner solar system. We learned that they were born in clouds of gas and dust, lived for millions or billions of years depending on their mass, and died in explosions so violent they could briefly outshine entire galaxies. We gave them distances. We measured them, catalogued them, mapped them across the sky in extraordinary detail. And for a moment it seemed like the universe was becoming knowable, like the mystery was giving way to understanding. But here is the thing most people never fully absorb. The more we learned about the stars, the farther away they turned out to be, and the farther away they turned out to be, the more unsettling the implications became. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That means the light leaving its surface right now will take 4 years and 3 months to reach your eye. 4 light-years sounds like a number, a measurement, something manageable. But consider what it actually means in physical terms. If you could travel at the speed of our fastest spacecraft ever launched, the Voyager 1 probe, which has been flying away from Earth for over 40 years, it would take you roughly 73,000 years to reach Proxima Centauri. 73,000 years. That is longer than modern human civilization has existed, and that is the nearest star. Now start to scale that outward. Our galaxy, the Milky Way, is 100,000 light-years across. It contains somewhere between 200 billion and 400 billion stars. The light from a star on the far side of our own galaxy has been travelling toward us for 100,000 years. It left its source before the last ice age ended, before Homo sapiens had spread across every continent, before the invention of agriculture, writing, or the wheel. It has been crossing the void for all of recorded human history and most of what came before it, and it is only just arriving now. And that is still inside our own galaxy. The nearest large galaxy to ours, the Andromeda Galaxy, is 2.5 million light-years away. 2.5 million years of continuous light travel. The light you can see from Andromeda on a clear dark night left its source when our ancestors were not yet fully human. When the creatures who would eventually become us were still learning to make simple stone tools on the African savanna, that light began its journey, and it has been flying through the darkness ever since, waiting for an eye that could recognize it. So when you look up at the sky, you are not seeing the universe as it is. You are seeing the universe as it was. Every single point of light in that sky is a message from the past. Some of those messages are a few years old, some are thousands of years old, some are millions, and the farthest objects we have ever detected, the most distant galaxies seen by our most powerful telescopes, their light has been travelling toward us for over 13 billion years. The universe itself is only 13.8 billion years old. That light began its journey almost at the very beginning of time. The source that sent it may not even exist anymore. The galaxy that produced it has likely changed beyond recognition. What you're seeing when you look at the edge of the observable universe is a relic, a fossil made of light. And here is where the mystery deepens. Here is where the feeling you had standing outside looking up becomes something more than wonder. Because we now know that the universe is not static. It is not a fixed stage on which stars and galaxies sit patiently in their places, waiting to be visited. The universe is expanding. Every galaxy beyond our local neighbourhood is moving away from us, carried outward by the growth of space itself. And the farther away a galaxy is, the faster it is receding. There is a distance, a specific calculable distance, beyond which galaxies are moving away from us faster than the speed of light. Not because anything is breaking the laws of physics, but because space itself is stretching, and when enough space is stretching between us and a distant object, the cumulative effect exceeds the speed at which light can cross it. This is the heart of what we're going to explore tonight. Not just the size of the universe, though the size alone is enough to stop your breath, but the nature of a universe that is expanding and accelerating in a way that makes certain destinations not merely distant, but permanently, fundamentally unreachable. The farthest star is not waiting for you at the end of a very long road. The road itself is growing. It is lengthening beneath your feet faster than you could ever walk it. And the star at the other end is not standing still. It is being carried away, gently and relentlessly and without pause, into a darkness that will eventually swallow it from our view entirely. Tonight, we are going to follow that idea all the way to its conclusion. through the structure of the cosmos, through the nature of dark energy, through the far future of the universe itself, until we arrive at the quiet, extraordinary truth of what it means to exist inside a cosmos that is always, in every direction, moving away from you. Before we can understand why the farthest star will always stay out of reach, we need to spend some time with light. Not just the idea of light, but the actual physical reality of what light is and what it does. Because light is not simply the thing that lets you see in the dark. Light is the only messenger the universe has ever had. It is the single medium through which information travels across the cosmos. Everything we know about everything beyond this planet, every star, every galaxy, every nebula, every black hole, every collision and explosion and birth and death happening out there in the dark. We know it because light brought us the news. And that fact, simple as it sounds, carries consequences that change everything about how we understand our place in the universe. Light travels at approximately 299,792 kilometers per second in a vacuum. That number is so large it is almost impossible to hold in your mind. In a single second, a beam of light can circle the entire Earth 7.5 times. In 8 minutes and 20 seconds, it travels from the surface of the Sun to your eye. In 1 year, it covers about 9.46 trillion kilometers. We call that distance a light year, and it has become the standard unit for measuring the cosmos because nothing else comes close to capturing the scale of what is out there. A light year is not a unit of time, it is a unit of distance. And it is a distance so enormous that it makes every other scale of measurement we use in daily life feel like a rounding error. But here is the part that matters most for what we are exploring tonight. Light travels fast, faster than anything else in the universe, and yet it still takes time to cross space. That time, multiplied across cosmic distances, creates a profound and disorienting truth. When you look at the moon, you are seeing it as it was 1.3 seconds ago. When you look at the Sun, you are seeing it as it was 8 minutes ago. When you look at Jupiter on a clear night, depending on where it sits in its orbit, you're seeing it as it was anywhere from 33 to 53 minutes ago. These are small delays, almost negligible. But as the distances grow, the delays grow with them, and the implications become impossible to ignore. The star nearest to our Sun, Proxima Centauri, is 4.24 light-years away. The light arriving at your eye from that star right now left its surface 4 years and nearly 3 months ago. You're not seeing Proxima Centauri as it is tonight. You're seeing Proxima Centauri as it was in the recent past, before this year began, before certain things in your own life had yet happened. Now extend that outward. The bright star Sirius, the most luminous star in our night sky, is 8.6 light-years away. The light from Sirius reaching you now left its source nearly 9 years ago. Betelgeuse, the great red giant at the shoulder of Orion, is approximately 700 light-years away. The light you see from Betelgeuse tonight has been travelling since the 1300s, when the medieval world was still untouched by the Renaissance. You're looking at a snapshot of a star taken 700 years before this moment. And this is just within our immediate neighbourhood of the galaxy. Move outward to the farthest stars visible to the naked eye, and the delays stretch into thousands of years. Look at the faint smudge of the Andromeda Galaxy, visible on a dark clear night as a tiny diffuse glow, and the light entering your eye has been in transit for 2.5 million years. It left its source before the genus Homo existed on Earth, before the first crude stone tools, before the first deliberate fire. The universe you see when you look up is not a portrait of the present. It is a layered archaeological record, with each layer receding deeper and deeper into the past the farther out you look. The night sky is a time machine, and every direction you point it takes you further back. Now, here is the thing most people do not fully sit with. If light takes time to reach us, then we can only ever see things as they were, never as they are. We have absolutely no way of knowing the present state of any object beyond our own solar system. The star you're watching right now might have exploded 1,000 years ago, and the light from that explosion is still centuries away from reaching us. There are stars in our catalogue that are, in the present moment of the universe, already dead, collapsed into neutron stars or black holes or scattered clouds of gas, and we will not find out for hundreds or thousands of years because the news is still on its way. The cosmos is full of objects we are watching in real time that have in reality already ceased to exist. You are mourning stars that have not yet told you they are gone. This is not a flaw in our instruments. This is not a gap in our technology that future telescopes will eventually close. This is a fundamental property of reality, because nothing, not radio waves, not gravity waves, not any known form of information transfer, travels faster than light. The speed of light is not just a speed limit for particles and spacecraft. It is the speed limit for knowledge itself. The universe can only tell you what happened somewhere else at the rate that light can carry the message. And when the distances involved span billions of light years, that message takes billions of years to arrive. By the time it gets to you, the sender is ancient history. So when we talk about seeing the farthest star, we need to be precise about what we mean. We are not seeing a star. We are receiving a very old signal. We're catching a photon, a single particle of light, that was emitted by a nuclear furnace an incomprehensible distance away, at an incomprehensible time in the past, and has been travelling through the expanding void ever since. That photon has crossed the spaces between galaxies, navigated the large-scale structure of the cosmos, threaded through the darkness for billions of years, and arrived at the lens of a telescope or the retina of an eye in this precise moment. Seeing it is a miracle of probability and patience, but seeing it is not the same as reaching it. Not even close. Seeing something means you have received its light. Reaching something means you can go there. And as we're going to discover over the course of this night, for the farthest objects in the universe, the gap between those two things is not just large, it is infinite. The messenger arrived, but the door it came from has already closed behind it and is moving further away every second. Before we travel beyond our galaxy, we need to stop here, right here inside the Milky Way, because most people, even people who love space, who read about it and watch documentaries and follow the latest discoveries, most people have not truly reckoned with the size of the galaxy we already live in. We talk about it constantly. We use the word casually. The Milky Way. It sounds almost gentle. A smear of pale light across a summer sky. Something soft and ancient and familiar. But the reality of what that smear actually represents is so extreme, so far beyond anything our intuition was built to handle, that sitting with it for a few minutes has a way of quietly rearranging something in the back of your mind. The Milky Way is a barred spiral galaxy. It has a dense central bulge, a flat rotating disk of stars and gas and dust, and a spherical halo of older stars extending above and below. From one edge of its disk to the other, it spans approximately 100,000 light years. 100,000 years of light travel end to end. Think about what that means. If you launched a spacecraft today moving at the speed of light, the absolute maximum speed that physics permits for anything carrying information, it would take 100,000 years to cross our galaxy from one side to the other. Not 100,000 kilometers, not 100,000 miles. 100,000 years of continuous travel at the fastest possible speed. The Milky Way is not a place you can cross. It is a scale you can only contemplate. Let us try to make this more concrete, because large numbers alone rarely land with the weight they deserve. The distance from Earth to the Sun, 150 million kilometers, a journey that takes light 8 minutes, is called 1 astronomical unit. It is the baseline measurement of our solar system. The entire solar system, from the Sun out to the orbit of Neptune, spans about 60 astronomical units across. Our nearest stellar neighbour, Proxima Centauri, is approximately 268,000 astronomical units away, or 4.24 light years. Now, take that distance, 4 light years, already a number that dwarfs our solar system by tens of thousands of times, and multiply it by roughly 24,000. That is how far the centre of the Milky Way is from where we sit right now. We are not near the centre. We are out in the suburbs, about halfway between the core and the outer edge, on a minor spiral arm called the Orion Arm. And even from this peripheral address, the galactic centre is 26,000 light-years away. The Milky Way contains somewhere between 200 billion and 400 billion stars. That range itself tells you something. The uncertainty spans 200 billion stars, which means we are not entirely sure of the count within a margin of 200 billion suns. Each of those stars is a nuclear furnace. Many of them have planets. Some of those planets almost certainly have conditions that could support liquid water. The sheer statistical weight of those numbers is staggering. And yet the stars, for all their billions, are not crowded together. Space is the dominant reality of the Milky Way. If you shrank the sun down to the size of a grain of sand, the nearest grain of sand, the nearest stars, would be roughly 4 kilometers away. The galaxy is almost entirely empty. It is a vast, dark ocean with scattered fires burning at enormous distances from one another, each one isolated in its own enormous bubble of nothing. Now consider what it would take to travel across this galaxy, not at the speed of light, but at the speeds we can actually achieve. The Voyager 1 probe, launched in 1977, is the most distant human-made object ever sent into space. After more than 40 years of continuous flight, it has travelled roughly 23 billion kilometres from Earth. That sounds impressive until you realise that 1 light year is approximately 9.46 trillion kilometres. Voyager 1 has covered less than 1/500th of a single light year. At its current speed, it would take approximately 73,000 years to reach Proxima Centauri, if it were headed in that direction, which it is not. To cross the full width of the Milky Way at Voyager speed would take on the order of 2 billion years. The galaxy is not a destination. It is a condition we exist inside without any realistic prospect of exploring more than the tiniest fraction of it. But here is the layer most people never add to this picture. Even if we could travel at the speed of light, the Milky Way would still take 100,000 years to cross. And during those 100,000 years of travel, everything would continue to change. Stars would be born and die. The galaxy itself would rotate. It completes one full rotation approximately every 225 to 250 million years, a span of time called a galactic year or cosmic year. The Sun has completed about 18 to 20 of these galactic years over its lifetime. The universe itself has only existed for about 60 galactic years. Our galaxy is not a static map. It is a living, rotating, slowly evolving structure, and a journey across it at the speed of light would span a time comparable to the entire rise and fall of complex life on Earth. And this, all of this, is just our galaxy. Just the one we happen to live in. The observable universe contains an estimated 2 trillion galaxies, 2 trillion structures, each one comparable in some way to the Milky Way, each one containing hundreds of billions of stars, each one separated from its neighbours by distances measured in millions or billions of light years. The Milky Way, with all its 100,000 light-year span and its hundreds of billions of fires, is a single grain of sand on a beach so vast we cannot see its edges. Understanding this is not a matter of memorising numbers. It is a matter of feeling the floor drop away beneath you, slowly and completely, as the true scale of things comes into focus. Because if our own galaxy, the one we live inside, the one whose centre we can see with the naked eye on a clear dark night as a faint band of light, is already this far beyond our reach, then what lies beyond it is something else entirely, something that requires a different kind of reckoning altogether, and that is exactly where we are going next. Step outside the Milky Way for a moment. Imagine you could pull back, far enough that our entire galaxy, with all its hundreds of billions of stars and its 100,000 light-year span, began to shrink beneath you, far enough that the Milky Way became a small, flattened spiral, pale and delicate, turning slowly in the dark. From this vantage point you would begin to see our neighbours, not nearby in any human sense, not reachable by any craft we have ever built, but close enough in the grand scheme of the cosmos to be considered part of the same community. The Milky Way does not exist in isolation. It exists inside a structure, a gravitationally bound collection of galaxies that astronomers call the local group, and the local group is the first step on a ladder of scale that climbs until the mind simply has nowhere left to stand. The local group contains more than 50 known galaxies, though the vast majority of them are small, dim dwarf galaxies that orbit the larger members like satellites around a planet. The two dominant members are the Milky Way and the Andromeda Galaxy, also known by its catalogue designation as Messier 31. Andromeda is a spiral galaxy like our own, somewhat larger, containing perhaps 1 trillion stars compared to our estimated 200 to 400 billion. It sits approximately 2.5 million light-years away. The light you can see from Andromeda on a clear moonless night, that faint smudged oval near the constellation Perseus, has been travelling toward you for 2.5 million years. It is the most distant object visible to the naked human eye, and yet in cosmological terms Andromeda is our closest major neighbour. It is practically next door. Andromeda and the Milky Way are in fact falling toward each other. The two galaxies are on a collision course, pulled together by their mutual gravity across the void between them. In approximately 4.5 billion years, They will begin to merge, a slow, staggering collision that will take hundreds of millions of years to complete, reshuffling stars and gas across vast distances and ultimately producing a single, larger elliptical galaxy that some astronomers have informally named Milkomeda. No stars will actually collide during this merger because the distances between individual stars are so enormous that even as two galaxies pass through each other, stellar collisions are vanishingly rare. But the gravitational disruption will be profound, and the shape and structure of both galaxies will be transformed beyond recognition. This collision is coming regardless of anything else in the universe. It is written into the math of gravity and time. Beyond the local group, the scale expands again. Our collection of more than 50 galaxies is itself part of a larger structure called the Virgo supercluster, also known as Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains the mass of approximately 100 million billion suns spread across a region roughly 500 million light-years in diameter. It includes thousands of individual galaxies, dozens of galaxy groups and clusters, all loosely connected by gravity into a single vast superstructure. The Milky Way sits near the outer edge of Laniakea, far from its dense core, the way a small town sits on the outskirts of a continent-spanning metropolitan region. Even within our own supercluster, we are peripheral. Even here, we are on the margins, and Laniakea itself is just one of millions of superclusters in the observable universe. When cosmologists map the large-scale structure of the cosmos, the universe at the very largest scales, hundreds of millions to billions of light-years across, what they find is breathtaking in its strangeness and its geometry. The universe is not uniformly filled with matter. It is structured like a vast three-dimensional web. Galaxies cluster together along thin filaments, long thread-like strands of matter and dark matter stretching across hundreds of millions of light-years. These filaments intersect at dense nodes where massive galaxy clusters accumulate, pulling in matter from all directions. And between the filaments, between the clusters and the superclusters, there are voids, enormous, nearly empty bubbles of space where almost nothing exists. No stars, no galaxies, barely any matter at all, stretching for hundreds of millions of light-years in every direction. The largest known void in the observable universe is called the Boots Void, sometimes nicknamed the Great Nothing. It is approximately 330 million light-years in diameter. If the Milky Way were located at the centre of the Boots Void, we would not have discovered the existence of other galaxies until the 1980s, because the nearest galaxy in any direction would have been so remote that our telescopes for most of the 20th century could not have detected it. The Bootes Void is not an anomaly, it is a feature. The cosmic web is laced with these enormous silent absences, and the matter of the universe, all the stars and galaxies and gas and dust, is threaded along the walls and filaments that define their boundaries, the way foam collects along the edges of bubbles in a vast and ancient ocean. This structure, the cosmic web, is one of the most beautiful and disorienting discoveries in the history of science. It emerged from the tiny quantum fluctuations that rippled through the universe in the first fraction of a second after the Big Bang. Those microscopic variations in density, stretched and amplified by cosmic expansion over 13.8 billion years, eventually became the filaments and voids and clusters we see today. The largest structures in the universe are the direct descendants of the smallest events at the very beginning of time. Every galaxy cluster, every supercluster, every shining filament in the cosmic web is a grown-up echo of a quantum tremor that occurred before stars existed, before atoms existed, in a universe so young and so hot that matter as we know it had not yet formed. And here is the thing that this picture makes undeniable. The universe is not a collection of objects sitting in empty space. It is a structure. A deeply interconnected, hierarchically organized structure, built on scales that range from the subatomic to the supergalactic, each level nested inside the next like a set of Russian dolls with no end in sight. We live inside a star system, inside a galaxy group, inside a supercluster, inside a filament of the cosmic web, inside the observable universe, which is itself, most likely, an infinitesimal region of a far larger whole. At every level of this hierarchy, the distances are vaster than our intuition can honestly hold, and yet all of it, the local group, the Virgo supercluster, the cosmic web in its entirety, is still only what we can see. still only the portion of the universe from which light has had enough time to reach us. What lies beyond that horizon is a question we'll spend the rest of this night beginning to understand. There is a boundary around you right now. You cannot see it. You cannot feel it. It has no physical substance, no wall, no membrane, no line drawn in the dark, and yet it is as real as anything in physics, and it defines the absolute limit of everything you could ever know about the cosmos from where you stand. This boundary is called the cosmic horizon, or the edge of the observable universe, and the moment you start to understand what it actually is, not just as a phrase, but as a physical reality, something shifts in the way the night sky feels, because the edge of the observable universe is not a place. It is a consequence. It is what happens when the age of the universe meets the speed of light, and the result is a sphere of knowability with you at the center and an impassable limit in every direction. Here is how it works. The universe is approximately 13.8 billion years old. That means light has had 13.8 billion years to travel since the Big Bang. You might expect, therefore, that the observable universe would have a radius of 13.8 billion light-years. The distance light could have covered in that time, but this is where the expansion of the universe introduces its first surprising complication. The universe has been expanding the whole time that light has been travelling through it. A photon emitted from a distant region of the early universe 13.8 billion years ago was not travelling through static space. It was travelling through space that was itself stretching and growing as the photon moved. By the time that photon reaches us today, the region of space it came from has been carried much farther away by cosmic expansion. The actual distance to the farthest objects whose light can currently reach us is not 13.8 billion light-years. It is approximately 46.5 billion light-years. That is the radius of the observable universe today. This number deserves a moment of quiet attention. 46.5 billion light-years in every direction, a sphere nearly 93 billion light-years across, with Earth, with you, at the centre of it. Not because Earth is special or cosmologically significant, but because the observable universe is observer-dependent. Every point in the universe has its own observable sphere around it, defined by what light has had time to reach from that specific location. An alien civilization in a galaxy 10 billion light-years away has a completely different observable universe than ours, overlapping with ours in some regions but centered on a different point, bounded by a different horizon. There is no single, universal map. There are only local spheres of knowability, each one centered on whoever is doing the observing. Now here is the part that most people do not think about when they hear the phrase edge of the observable universe. What lies beyond it? The honest answer is that we do not know, and more importantly, we cannot know by definition, because no information from beyond that boundary has had time to reach us yet. The universe beyond our cosmic horizon may contain more galaxies, more stars, more structure identical to what we see within our sphere. Most cosmologists believe it does, and that the total universe is vastly larger than the observable portion, perhaps infinitely larger, depending on the geometry of space on the grandest scales. But we have no direct evidence of any of it. Everything beyond 46.5 billion light-years is, from our perspective, as absent as if it did not exist. The horizon is not a wall, it is a silence. There is another subtlety here that is worth sitting with. The cosmic horizon is not fixed. It is not a permanent boundary set in stone at the moment of the Big Bang. It changes over time. As the universe ages, light from more distant regions has more time to reach us, and in principle, the observable universe grows. In a universe expanding at a constant rate, you might expect that over time we would eventually see more and more of what lies beyond our current horizon. But here is the terrifying complication. The expansion of the universe is not constant, it is accelerating. Space is stretching faster and faster, driven by the mysterious force known as dark energy. And this acceleration means that distant regions of the universe are receding from us at ever-increasing speeds. There are already galaxies well within our current observable universe whose light, emitted today, will never reach us, because the space between us and them is expanding faster than light can cross it. The horizon is not just a limit on our past, it is closing in on our future. This is a concept so strange that it is worth repeating carefully. There are galaxies we can see right now, galaxies that are currently visible in our telescopes, that we will never be able to exchange a signal with again. The light we see from them is ancient light that left those galaxies billions of years ago, when the universe was younger and expanding more slowly, when the distance between us was small enough for light to make the crossing. But any light emitted from those galaxies today is fighting against an expansion it cannot overcome. It will never arrive. We received their old messages, but we cannot send new ones, and they cannot reach us with anything more recent. We are already, in a very real sense, cosmologically cut off from a significant portion of what we can currently see. The edge of the observable universe is therefore not simply a distance. It is a statement about connection and isolation. It is the universe telling us what we can be in contact with and what we cannot. Within the horizon, information can flow, slowly, across vast distances and enormous spans of time, but it can flow. Beyond the horizon, and increasingly for the regions approaching it, connection is severed, permanently. Not by distance alone, but by the combination of distance and acceleration, by the way the universe is actively pulling things beyond the range of any possible communication. You are at the centre of a sphere of knowability that is, in some directions, already shrinking relative to what you could once have reached. The universe has edges, and those edges are moving. Lying in the dark tonight, consider that image. A sphere of light and information surrounding you in every direction, 46.5 billion light-years to its edge. And beyond that edge, a darkness that is not empty, that is almost certainly full of stars and galaxies and structures as magnificent as anything we have ever seen. But that is unreachable not because it is too far, and not because we lack the technology, but because the universe's own expansion has placed it outside the reach of any possible signal, any possible journey, any possible knowing. The edge of the observable universe is the universe telling you, with quiet and absolute finality, that some things will always remain beyond the horizon, and we have not yet arrived at the most terrifying part of that sentence. In the year 1995, astronomers made a decision that many people at the time considered wasteful, even reckless. They took the Hubble Space Telescope, the most expensive and celebrated scientific instrument ever placed in orbit, and they pointed it at a patch of sky near the handle of the Big Dipper, not at a known galaxy, not at a dramatic nebula or a spectacular star cluster, at nothing, at a region of sky so apparently empty that it contained no catalogued objects of any significance. They held it there, completely still, for 10 consecutive days. The telescope collected every photon that passed through its lens from that tiny, dark, featureless square of sky, a region so small it would be covered by a grain of sand held at arm's length, and when they processed the image, the scientific community went silent with awe. That patch of apparent nothingness contained approximately 3,000 galaxies. That image became known as the Hubble Deep Field. It was the first time humanity had looked that deeply and that patiently into the universe, and what it revealed was staggering. Every smear and spiral and elliptical blob in that image was an entire galaxy, a system of hundreds of billions of stars, many of them older than our Sun, all of them at distances almost too large to articulate. Some of the galaxies in that image were so far away that their light had been travelling for more than 12 billion years before it entered Hubble's lens. The universe was suddenly undeniably full, not just full of stars within our galaxy, but full of galaxies, full of entire universes of stars stacked behind one another in every direction, layer upon layer upon layer, receding into the deep past with no apparent end. The Hubble Deep Field did not just expand our sense of scale, it transformed it completely. In the years that followed, astronomers pushed deeper. The Hubble Ultra Deep Field, released in 2004, looked at an even smaller patch of sky for even longer, over 11 days of cumulative exposure time, and revealed approximately 10,000 galaxies in a region of sky smaller than 1/13 millionth of the total sky area. Then came the Hubble Extreme Deep Field in 2012, which combined and refined data from earlier observations to reveal galaxies as far as 13.2 billion light-years away, objects whose light left their source when the universe was only about 600 million years old, a mere 4% of its current age. These were not fully formed, majestic spirals. They were small, irregular, chaotic proto-galaxies, furiously forming stars in the turbulent early universe, captured in a snapshot so old that the cosmic structures we are familiar with today had barely begun to coalesce. But even these record-breaking observations were eventually surpassed. On July 12, 2022, NASA released the first full-color science images from the James Webb Space Telescope, the most powerful space observatory ever built. The first image released, known as Webb's First Deep Field, showed galaxy cluster SMAC 0723 as it appeared 4.6 billion years ago, with the gravitational mass of the cluster acting as a lens, bending and magnifying the light of even more distant galaxies behind it into bright curved arcs. In a single image, the James Webb Telescope revealed objects whose light had been travelling for over 13 billion years. The resolution and depth were unlike anything achieved before. Galaxies that had previously been invisible smudges were suddenly resolved into detailed structures, spiral arms, star-forming regions, ancient cores of dying stars. Then, in 2023, using data from the James Webb Space Telescope, astronomers confirmed the detection of a galaxy designated JADES-GS-Z 140. This galaxy existed when the universe was only about 290 million years old, just 2% of its current age. Its light has been travelling toward us for over 13.5 billion years. It is one of the earliest and most distant objects ever confirmed. And it was not a simple, featureless smudge. It was already producing stars at a remarkable rate, already more massive than models had predicted any galaxy could be so early in cosmic history. Its very existence challenged assumptions about how quickly the universe was able to form large structures after the Big Bang. The farthest things we can see are not just records of distance. They are puzzles. They are clues to a universe whose early history we do not yet fully understand. There is also the story of a single star, not a galaxy, but one individual star, that briefly held the record for the most distant stellar object ever detected. In 2022, astronomers using the James Webb Space Telescope and gravitational lensing confirmed the observation of a star they named Earendel, discovered originally by Hubble. Earendel is a massive hot blue star located approximately 12.9 billion light-years away. Its light left its source when the universe was less than a billion years old. Earendel is not a galaxy. It is a star, a single nuclear furnace, burning alone in the ancient universe. And we can see it only because the gravitational mass of an intervening galaxy cluster bent and amplified its light toward us with extraordinary precision. Without that cosmic magnifying glass, it would be utterly invisible. Earendel is the oldest, most distant individual star we have ever detected, and it is almost certainly long dead. This is the thing about the farthest light ever seen. Every record we set, every new depth we peer into, every galaxy and proto-galaxy and ancient star we pull out of the cosmic dark. They are all showing us the same fundamental truth from different angles. The universe is ancient and it is vast, and the farthest things we can see are so remote in both space and time that they belong to a different era of cosmic history. They are not part of the same universe we inhabit in any practical sense. They are fossils, archaeological layers, messages in a language that took billions of years to arrive, describing a universe that no longer exists in the form it had when those messages were sent. We receive them. We read them with our telescopes and our mathematics and our patient, wandering minds. But we are reading letters from a cosmos that has long since moved on. The authors are gone. The places they described have changed beyond recognition. And the distance between us and the source of that oldest light is not just the farthest we have ever seen. It is, in the most profound sense, the farthest anything can ever be seen from here. The outer boundary of what the universe has allowed us to know. The year was 1929. An American astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California, using what was then the most powerful telescope in the world to study the faint smudges of light that some astronomers were calling nebulae, and others were beginning to suspect were entire galaxies, island universes far beyond the boundaries of the Milky Way. Hubble had already done the extraordinary work of confirming that these smudges were indeed separate galaxies, unimaginably distant from our own. But now he was looking at something else in the data, something that nobody had quite put together in a clear, unified way before. He was looking at the velocities of those galaxies, at how fast they were moving and in which direction, and what he found rearranged the foundations of cosmology forever. Almost every galaxy Hubble measured was moving away from us. Not a few of them, not most of them. Almost all of them, in almost every direction, were receding. And more than that, the farther away a galaxy was, the faster it was moving away. This relationship, now known as Hubble's law, revealed something profound and initially difficult to accept. The universe was not static. It was not the fixed, eternal, unchanging stage that most scientists and philosophers had assumed it to be. It was expanding. Space itself was growing, carrying galaxies away from each other the way raisins in a rising loaf of bread move apart, not because the raisins are moving through the dough, but because the dough itself is expanding. No galaxy is moving through space toward some distant edge. The space between galaxies is simply becoming more space, continuously and in every direction simultaneously. This discovery had an immediate and staggering implication. If the universe is expanding now, then in the past it must have been smaller. Wind the clock backward, and the galaxies converge. Wind it back far enough, and all the matter and energy in the observable universe was compressed into an unimaginably small, unimaginably hot and dense state. The expansion we see today is the ongoing echo of that original event, the Big Bang, which occurred approximately 13.8 billion years ago. Hubble's observation of expanding galaxies was not just a discovery about the present state of the cosmos. It was a discovery about its origin, its history, and its ultimate fate. The universe has a story, and expansion is its central plot. For decades after Hubble's discovery, the prevailing assumption was that the expansion was slowing down. This seemed intuitively obvious. Gravity is the dominant force on cosmic scales, and gravity is attractive. It pulls matter together. All the mass in the universe should be exerting a gravitational brake on the expansion, decelerating it over time, the way a ball thrown upwards slows as it rises. The open question was whether there was enough mass to halt the expansion entirely and eventually reverse it, leading to a big crunch, a catastrophic collapse back to a singularity, or whether the expansion would continue forever, slowing but never quite stopping, as the universe spread itself thinner and thinner across an infinite dark void. Either way, deceleration was assumed. The expansion was expected to be losing momentum. Then came 1998, and one of the most shocking discoveries in the history of science. Two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were using a specific type of stellar explosion called a Type 1a supernova to measure cosmic distances with extraordinary precision. Type 1 supernovae are useful because they always explode with approximately the same intrinsic brightness, making them reliable distance markers, what astronomers call standard candles. By comparing how bright these supernovae appeared against how bright they should be, the teams could calculate exactly how far away they were, and therefore map the expansion rate of the universe across billions of years. Both teams expected to find evidence of deceleration. Instead, they found the opposite. The distant supernovae were dimmer than expected. They were farther away than they should have been if the expansion was slowing down. The expansion of the universe was not decelerating, it was accelerating. The universe was not just expanding, it was expanding faster and faster with each passing moment. The teams initially doubted their own results. The finding was so counterintuitive, so at odds with everything that gravitational physics predicted, that both groups spent months checking and rechecking their data, looking for errors, searching for any alternative explanation. There was none. The acceleration was real, and its implications were terrifying in the most precise sense of that word. Something was driving the expansion of the universe to speed up. Something was overpowering gravity on the larger scales, pushing space apart with increasing force, working against every known attractive interaction in the cosmos. That something was given a name, dark energy. But the name was, in a sense, a placeholder for ignorance. We called it dark energy because it was dark, meaning invisible and undetected by any instrument, and energy because it had to have some form of energy density to produce the effect we were measuring. But what it actually was, what its physical nature might be, nobody knew then, and nobody knows today. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for this discovery. The prize was well deserved. What they had found was not just a new phenomenon, it was a new regime of physics, a new dominant force in the universe that had been invisible to us until we looked far enough and carefully enough to detect its fingerprints. Dark energy, according according to current measurements, makes up approximately 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. Everything else, all the ordinary matter that makes up stars, planets, gas, dust, you, and everything you've ever touched or seen or thought about, constitutes approximately 5% of what exists. The universe is mostly made of things we cannot see and do not understand, and the dominant component is actively tearing it apart. Here is what the accelerating expansion means in the context of what we've been exploring tonight. It means that the farthest objects in the universe are not merely distant, they are receding. They are being carried away from us by the growth of space at speeds that increase over time. Objects that are already beyond a certain distance, the Hubble radius, located roughly 14 billion light-years away, are receding from us faster than light, not because they are moving through space at superluminal speeds, which would violate relativity, but because so much space exists between us and them that the cumulative stretching of all that space adds up to a recession velocity exceeding the speed of light. This is not a technicality, it is a physical reality with a physical consequence. The light those objects emit today will never reach us. The gap between us is growing faster than any signal can cross it. And because the expansion is accelerating, more and more of the universe is crossing that threshold every moment, slipping permanently beyond the boundary of what can ever be known or reached from here. Let us run a thought experiment together. Imagine, for a moment, that the laws of physics bent just enough to grant you something impossible, a spacecraft capable of travelling at the speed of light. Not approaching it, not a fraction of it, but at it, the full 299,792 kilometers per second, sustained indefinitely, with unlimited fuel and perfect engineering. You point this vessel toward the farthest galaxy you can detect, the one whose ancient light has just barely reached your telescope after travelling for 13 billion years across the expanding cosmos. You fire the engines, you begin, and here is the question that matters. Do you arrive? The answer, when you work through the mathematics honestly and completely, is no. You do not arrive, you cannot arrive. And the reason why is one of the most quietly devastating truths the universe contains. To understand why, we need to think carefully about what is happening to the space between you and your destination while you are travelling. Space is not a passive backdrop. It is not an empty container that sits still while objects move through it. Space is dynamic. It stretches, it grows, and in our universe driven by dark energy, it grows faster over time, not slower. So while you're flying at the speed of light toward that distant galaxy, the space between you and it is expanding. More space is being created between you and your destination every second of your journey. The galaxy is not simply sitting at a fixed distance, waiting for you to close the gap. It is being carried away from you by the expansion of space itself, and the rate at which it recedes increases the farther away it is. For galaxies within a certain range, within what is called the Hubble radius, approximately 14 billion light-years away, the recession velocity due to expansion is less than the speed of light. In principle, a beam of light emitted from Earth today will eventually reach those galaxies, even though they are receding, because the light is moving through the expanding space fast enough to make net progress. It is like swimming against a current that is not quite strong enough to push you back. Slow going, but eventually you get there. Beyond the Hubble radius, however, the recession velocity exceeds the speed of light, and a photon emitted today makes no net progress toward those objects. The current is too strong. The space is growing faster than light can cross it. Those objects are, today, already beyond the reach of anything we could send toward them, no matter how fast. But here is where it becomes even more unsettling. The Hubble radius is not the outer boundary of what was reachable in the past. Because the universe was younger and expanding more slowly in earlier epochs, there are galaxies currently beyond the Hubble radius whose ancient light has already reached us. Light that was emitted billions of years ago, when those galaxies were much closer, when the expansion had not yet carried them so far. We can see them, we have received their old messages, but anything emitted from those galaxies today, aimed at us, will never arrive, and anything we send toward them today will never arrive either. We are looking at objects we can never contact again. The communication channel is permanently closed, even as we continue to receive the last echoes of a connection that ended long ago. Now bring your imaginary light-speed spacecraft back into the picture and point it not at the very edge of the observable universe, but at something somewhat closer. A galaxy, say, 10 billion light-years away. You launch. You travel at the speed of light for 10 billion years. But during those 10 billion years, the universe continues to expand, and it expands at an accelerating rate. The galaxy you were aiming for has moved. Not by accident, not because it had engines of its own, but because the space between you and it kept growing throughout your entire journey. When you crunch the numbers, and cosmologists have done exactly this, you find that for galaxies beyond a certain threshold, called the cosmic event horizon, even a light-speed journey begun today will never close the gap. The destination recedes faster than you can approach. You travel for billions of years and arrive at empty space, because your target was carried away while you were in transit. The cosmic event horizon sits at a distance of approximately 16 billion light-years from us today. Anything currently beyond that boundary cannot be reached by anything we send out, ever, regardless of speed. Not because of any physical barrier, not because of any wall or force field or obstruction, but because space itself, expanding at an accelerating rate, ensures that the gap will always grow faster than any traveller or any beam of light can close it. The event horizon is not a place. It is a mathematical consequence of the universe's expansion history and its future trajectory. It is the universe's way of saying, with elegant and indifferent finality, that some destinations were always going to be impossible. There is something philosophically profound about this that I want you to sit with for a moment. We are not limited by our technology. We are not limited by our ambition or our intelligence, or our willingness to endure the staggering duration of an interstellar voyage. We are limited by the geometry of the universe itself. The speed of light is the maximum speed at which information or matter can travel. The universe's own hard limit, built into the structure of space-time by the laws of relativity. And yet even that maximum speed is not enough. The universe has arranged things such that its own expansion outruns even the fastest thing that physics permits to exist. It is as if the cosmos drew a circle around you and then, quietly and without announcement, began making that circle smaller. Not the circle of what you can see, the circle of what you can ever touch. And the expansion is accelerating, which means the situation worsens over time. Every year that passes, the cosmic event horizon encompasses a slightly smaller region of the universe from our perspective. Galaxies that are today just barely within theoretical reach are being nudged, year by year, closer to the threshold beyond which they will cross permanently into unreachability. Future generations, if they exist, will inherit a slightly more isolated cosmos than the one we inhabit. The universe is not standing still while we deliberate. It is actively, continuously, and with increasing urgency placing more and more of itself beyond the horizon of what anything originating here could ever reach. Speed, in the end, is not the answer, because the question the universe is asking is not how fast you can go. It is asking whether the space you're trying to cross will cooperate, and increasingly, emphatically, it will not. There is something in the universe that we cannot see, cannot detect directly, cannot touch, or measure or sample or photograph, and yet it makes up approximately 68% of everything that exists. It is not matter. It is not light. It is not any particle that our most sensitive instruments have ever caught a trace of. It has no known source and no accepted theoretical explanation that every physicist agrees on. We know it is there only because of what it does, because of the relentless, accelerating expansion it drives, the way it pushes space apart at an ever-increasing rate, the way it overrules gravity on the larger scales and pulls the universe in the opposite direction from everything we would expect. We call it dark energy, and of all the strange and humbling discoveries that modern cosmology has produced, dark energy may be the strangest and most humbling of them all. The concept has a history that stretches back further than the 1998 supernova discoveries. Albert Einstein, when he first applied his general theory of relativity to the universe as a whole in 1917, found that his equations predicted a dynamic universe, one that was either expanding or contracting, but not static. This troubled him, because at the time the scientific consensus was that the universe was fixed and eternal, so he introduced a term into his equations called the cosmological constant, a kind of repulsive energy built into the fabric of space itself, a pressure that would counteract gravity and hold the universe in a stable, unchanging state. When Hubble demonstrated in 1929 that the universe was in fact expanding, Einstein famously called the cosmological constant his greatest blunder and removed it from his equations. What nobody knew at the time was that the cosmological constant, or something very much like it, was real after all. Einstein had introduced it for the wrong reason, abandoned it for a good one, and been accidentally correct in a way that would not be confirmed for another 70 years. Today, the cosmological constant is the simplest mathematical description of dark energy, and it corresponds physically to the idea that empty space itself has an intrinsic energy density. Even a perfect vacuum, a region containing no particles, no radiation, no matter of any kind, has energy. Not nothing. Something. Space in this picture is not truly empty. It is filled with a baseline energy that is uniform across the entire universe, that does not dilute as the universe expands, and that exerts a constant outward pressure on space itself. As the universe grows, and the matter within it becomes more spread out and gravity becomes weaker over larger distances, this intrinsic energy of the vacuum begins to dominate, and once it dominates, it drives an acceleration that compounds over time, pushing space apart faster and faster in a process that has no natural endpoint. Dark energy does not run out. It does not weaken. It is, as far as we can tell, a permanent and growing feature of the cosmos. But the cosmological constant is only one possible explanation for dark energy, and it comes with a problem so severe that physicists sometimes call it the worst prediction in the history of science. When quantum field theory, our best framework for understanding the behavior of particles and energy at the smaller scales, attempts to calculate the energy density of the vacuum, it produces a number. That number, compared to the observed value of dark energy measured through cosmic expansion, is wrong by a factor of somewhere between 10 to the power of 60 and 10 to the power of 1 of 60 and 10 to the power of 120. Those are not small discrepancies. They represent the largest mismatch between theory and observation in all of physics. Something is profoundly incomplete about our understanding, either of quantum fields, or of gravity, or of both. Dark energy is real. Its effects are measured. But why it has the value it has, why the vacuum energy is not astronomically larger or smaller than what we observe, remains one of the deepest unsolved problems in all of science. Alternative explanations have been proposed. Some physicists suggest that dark energy is not a fixed constant but a dynamic field, something called quintessence, that changes in strength over time and varies across space. If quintessence is real, then the fate of the universe depends on how that field evolves. It could weaken, or it could intensify, or it could fluctuate in ways that produce a dramatically different cosmic future than the one simple acceleration predicts. Some theories suggest that dark energy could eventually grow strong enough to overcome not just intergalactic gravity, but the gravity holding galaxies together, then the gravity of solar systems, then the electromagnetic forces holding matter together in a final catastrophic event called the Big Rip, a moment when the expansion of space tears apart everything, right down to atoms and subatomic particles in a finite span of time. Other theories suggest the opposite, that dark energy might fade, allowing gravity to reassert itself and the universe to collapse. We do not know which scenario is correct. We do not yet have the tools to distinguish between them with certainty. What we do know, with confidence built from decades of precise cosmological measurement, is that right now, in the universe as it currently exists, dark energy is winning. It is the dominant force at cosmological scales. It is the reason galaxies beyond our local neighborhood are receding. It is the reason that recession is accelerating. It is the reason the cosmic horizon is a shrinking boundary rather than an expanding one. And it is the reason that the great silence growing between stars and galaxies is not merely the silence of distance. It is the silence of increasing, deliberate, cosmically enforced separation. The universe is not just large. It is becoming more isolated, piece by piece, galaxy by galaxy, with every moment that passes. Consider what this means in purely physical terms, stripped of abstraction. Right now, as you lie in the dark listening to these words, every galaxy beyond our local group is moving away from us. The Virgo cluster, 65 million light-years away, is receding. The Coma cluster, 320 million light-years away, is receding faster. The farthest galaxy clusters we can detect are receding so fast that the space between us grows by more than the speed of light every second. And this is happening in every direction simultaneously, above you, below you, to every side. The universe is expanding around you like an inflating sphere with no center and no edge, and dark energy is the pressure inside that sphere, and it has been building for billions of years with no sign of relenting. The great silence growing between stars is not a poetic metaphor. It is a physical measurement. The universe is becoming quieter, not because anything is being destroyed, but because everything is being separated. Light that could once make the crossing between distant regions of the cosmos in 1 billion years will one day require 10 billion, then 100 billion, then will never arrive at all. The signals are fading not because the senders are going dark, but because the receivers are being carried away beyond all possible range. Dark energy is not dramatic. It does not announce itself. It does not roar or flash or leave a scar across the sky. It simply, quietly, and without pause makes more space. And in making more space, it makes more silence. An endless, growing, cosmic silence that is, in its patient and indifferent way, the most terrifying force the universe contains. Imagine living on an island. Not a small island, an enormous one, rich with life and complexity, full of mountains and forests and rivers and everything you could ever need. But an island nonetheless, surrounded by an ocean that stretches in every direction as far as any instrument can detect. Now imagine that the ocean is rising, not fast enough to threaten you today, or tomorrow, or in your lifetime, but rising steadily, persistently, and at an accelerating rate. And as it rises, the mountains of distant continents that you could once see on clear days begin to disappear below the waterline one by one, slipping beneath the horizon, gone not because they cease to exist, but because the water between you and them has grown too deep, too wide, too absolute to see across. This is, in the most precise metaphorical sense I can offer, what is happening to the observable universe right now. The horizon is not expanding outward to reveal more. It is effectively contracting, swallowing our view of the cosmos galaxy by galaxy, supercluster by supercluster, in a process that has already begun and will never reverse. We established earlier that the observable universe spans roughly 46.5 billion light-years in radius, the sphere within which light has had time to reach us since the Big Bang. In a universe without dark energy, without accelerating expansion, this sphere would grow over time. As the universe aged, light from ever more distant regions would have enough time to complete the journey, and our observable bubble would slowly encompass more of the cosmos. More galaxies would come into view, more structure would become detectable. The universe would become, in a very gradual and patient way, more knowable. But we do not live in that universe. We live in one where dark energy is accelerating the expansion, and in that universe the situation is precisely reversed. The effective horizon, the boundary beyond which signals sent today will never reach us, is not growing. It is shrinking relative to the total size of the cosmos, and the galaxies currently visible to us are, one by one, being carried beyond the point of no return. The process is already well underway. Astronomers can calculate, based on current measurements of the expansion rate and the properties of dark energy, which galaxies are in the process of crossing our cosmic event horizon right now. Galaxies in the far reaches of the observable universe, objects we can currently detect with our most powerful telescopes, are receding from us at velocities that already exceed the speed of light due to the cumulative expansion of space. The light we receive from them today is ancient light, emitted when those galaxies were much closer, when the expansion had not yet carried them so far. But any new light they emit, any signal, any event occurring in those galaxies in the present moment of the universe, will never reach us. The connection has already been severed. We are simply still receiving the old messages, unaware that the channel closed long ago. Over the next few billion years, this process will become visually apparent, not to human eyes, which will not exist to witness it, but in principle to any sufficiently advanced observers who might be present. Galaxies that are currently part of our distant but detectable universe will gradually redshift beyond the range of any instrument. Their light will stretch to longer and longer wavelengths as the expansion carries them away, from visible light to infrared, from infrared to microwave, from microwave to radio waves too long and too faint to detect. They will not blink out suddenly, they will fade, Slowly, over billions of years, each galaxy will dim and redden and stretch until it crosses the threshold of detectability, and then it will be gone. Not destroyed, not dead, simply beyond reach and beyond sight, existing in a region of space that has become permanently disconnected from ours. The timescales involved are difficult to hold in mind. In approximately 150 billion years, roughly 10 times the current age of the universe, nearly all galaxies beyond our local group will have receded beyond our cosmic event horizon. The night sky, for any observers existing at that remote future epoch, will be essentially empty of external galaxies. The Milky Way and its gravitationally bound companions will still exist, merged and reorganized by then into a single large elliptical galaxy. But the vast cosmic web we can map today, the filaments, the clusters, the superclusters, the 2 trillion galaxies spread across the observable universe, will have vanished from view. Future observers will look out into a darkness interrupted only by the stars of their own merged galaxy. They will have no way of knowing that beyond that darkness lies the rest of the universe, carrying on in its own isolated bubbles, forever out of reach and forever out of sight. This is perhaps the most chilling implication of accelerating expansion. It does not merely make the universe unreachable, it will eventually make it unknowable. A civilization arising in that far future will have access to only a tiny fraction of the evidence that we have today. They will observe their own galaxy, perhaps deduce from its internal physics that stars are powered by nuclear fusion and that the cosmos is old. But the cosmological clues that led us to discover the Big Bang, the expansion of the universe, the existence of other galaxy clusters and superclusters, those clues will be gone. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills our sky today, with information about the early universe, will have redshifted to wavelengths too long and too faint to detect. The recession of distant galaxies, which told Hubble that the universe was expanding, will be unobservable because there will be no visible galaxies to measure. Future civilizations may be cosmologically blind in ways we cannot fully appreciate, and they will not even know what they are missing. Some cosmologists have described this as a kind of cosmic tragedy. Not for us. We live at a remarkably privileged moment in the history of the universe, early enough that the cosmic web is still visible, that the evidence for the Big Bang is still detectable, that the full splendor and scale of the cosmos is still within the range of our instruments. We are, in a very real sense, living in the golden age of cosmological observation. The universe is still legible, the clues are still present, the story of creation is still written across the sky for any eye patient and curious enough to read it. But that window is closing. Not today, not in any human time frame, but in the deep future of the cosmos, the sky will empty, and the story will become unreadable. The universe will continue to exist, but its past and its structure will be locked away behind horizons that no intelligence, however advanced, can ever penetrate. What we know now, what we have managed to piece together in our brief, extraordinary moment of cosmic awareness, may be the most complete picture of the universe that any mind will ever have. And that picture shows a cosmos in the process of sealing itself away, one vanishing galaxy at a time. Let us try something different. Let us set aside the mathematics for a moment and simply imagine the journey. Not as an equation or a cosmological model, but as an experience, as something a conscious being might actually attempt, might actually feel, might actually endure. Because there is something important in the trying, even when the trying is doomed. There is something the thought experiment reveals about the nature of the universe that the equations alone do not fully convey. So close your eyes or let them rest and come with me. We are going to attempt the impossible journey. We are going to aim for the farthest star we can see and simply go. We leave Earth behind. The solar system shrinks beneath us. First the inner planets, then Jupiter and Saturn hanging in the dark like distant lanterns, then the outer planets, then the long cold quiet of the Oort cloud, the spherical shell of frozen debris that marks the gravitational boundary of our sun's influence. We are already in a place no human has ever been. The sun behind us is still the brightest star in our sky, but it is fading. Ahead the stars are distributed with perfect indifference. No sign that any direction is better than any other, no cosmic landmark pointing toward our destination. We set our course toward a galaxy at the edge of the observable universe, 13 billion light-years away, and we accelerate to a speed as close to the speed of light as physics will allow. The journey has begun. The first thing we encounter is the void. The space between stars, even within our own galaxy, is almost incomprehensibly empty. There is no air, no dust, no debris in any meaningful density, just the occasional hydrogen atom drifting in isolation, and the faint electromagnetic wash of background radiation pressing against us from all directions equally. The silence is not like any silence you have experienced on Earth, where the absence of sound is still filled with the subtle presence of air and proximity and life. This is a different kind of silence, complete, structural. A silence that is not the absence of noise, but the presence of nothing. We travel through the galaxy for 100,000 light years, which at near light speed, thanks to the time dilation that special relativity provides, might feel compressed subjectively. But from the perspective of the universe, 100,000 years are passing outside our vessel. We exit the Milky Way. Now the void becomes something else entirely. Between galaxies, there is even less than between stars. The intergalactic medium, the thin, hot, diffuse plasma that fills the spaces between galaxy clusters, has densities so low that a cubic meter of it might contain less than one atom on average. We are in the deepest desert the universe contains. The Milky Way recedes behind us, shrinking from a full galactic disk to a faint smudge, to a point of light indistinguishable from any other. Ahead, across 2.5 million light-years of darkness, Andromeda glows faintly. We pass through its neighbourhood and continue. The local group falls behind. We enter the intergalactic void in earnest, and the darkness around us becomes a thing of extraordinary weight and totality. Billions of years pass outside our ship as we travel at near light speed, and here is where the thought experiment begins to reveal its terrible secret. We've been monitoring our destination, the galaxy we chose, the one whose ancient light we detected from Earth. We have been watching it, and something is wrong. It is not getting closer at the rate we expected. It is receding. Not because it is moving through space, but because the space between us and it is growing. Dark energy is at work, as it always is, as it has always been, quietly and relentlessly adding more space between every point in the universe. We are travelling at nearly the speed of light, and our destination is retreating. Not faster than us, not yet. We are still making net progress, at least for now. But the rate at which we close the gap is diminishing. The universe is working against us with increasing force. More billions of years pass. The universe around us changes. Stars that were visible when we departed have aged and died. The stellar populations of the galaxies we pass have shifted. The brilliant blue giants that once lit up young galaxies have burned out, and the older, redder, quieter stars have come to dominate. The universe is aging around us as we fly through it, and the destination still ahead is still retreating. We run the calculations again. The galaxy we are chasing is now receding faster than it was before. Not because it has accelerated through space, but because the cumulative expansion of all the space between us has grown so large that the recession velocity has increased. We are in a race with geometry itself, and geometry is pulling ahead. At some point in the journey, and cosmologists can calculate roughly when this occurs for different starting distances, the math tips over. The destination begins to recede faster than we can approach it. Not all at once, not with any dramatic announcement, just a gradual, inevitable tipping of the scales, as the expansion of space exceeds our velocity by a margin that grows larger with every passing moment. We are still moving. We are still trying. Our engines have not failed, and our course has not wavered. But we are losing ground. The galaxy is ahead of us and moving away faster than we are moving toward it, and no increase in speed, even if we could somehow exceed our current near-light velocity, which we cannot, would change this outcome. The destination is gone, not destroyed, not vanished, simply placed by the architecture of an accelerating universe, permanently beyond our reach. The thought experiment ends here, not with a crash or an explosion or any dramatic conclusion, but with a quiet and total impossibility. You're in the middle of an intergalactic void, billions of light years from anything familiar, billions of years into the future, travelling at the maximum speed the universe permits, and your destination is still moving away. There is nothing left to try. No course correction, no additional thrust, no clever manoeuvre through space-time that changes the fundamental outcome. The farthest star was never waiting for you at the end of a very long road. It was always receding, always being carried further away by the expansion of space, always subject to the same dark energy that has been reshaping the cosmos since long before you began. The journey was not a failure of will or technology or courage. It was a collision with the deepest rule the universe contains. Some places are not destinations, they're directions, things you can point toward forever, moving closer to them never, while the universe calmly and completely disagrees with your ambition. After everything we have explored tonight, the accelerating expansion, the shrinking horizon, the impossible journey, the universe closing itself off galaxy by galaxy, it would be easy to arrive at a feeling of pure, unrelieved desolation. A sense that the cosmos is nothing but an exercise in futility, a stage designed to display the smallness and limitation of everything that lives within it. But that is not the complete picture, because the universe, for all its vast indifference, has also done something quietly generous. It has left us a neighbourhood, a gravitationally bound collection of galaxies that dark energy cannot tear apart, that will remain connected and in principle reachable across the full span of time, a cosmic home that, while small against the backdrop of the total universe, is by any measure we might honestly apply to our own existence, almost incomprehensibly large. We are not entirely marooned. We are simply living on a very large island in an ocean that is growing faster than any boat can cross it. The key concept here is gravitational binding. Dark energy works by driving the expansion of space, pushing unbound structures apart at an accelerating rate. But gravity, on smaller scales and between objects with sufficient mass in proximity, can overcome that expansion. When two objects are close enough and massive enough relative to the space between them, their gravitational attraction exceeds the tendency of dark energy to push them apart. They remain bound. They orbit each other, merge, interact, connected across time in ways that the broader cosmic expansion cannot interrupt. The threshold between bound and unbound is not arbitrary. It is written into the mathematics of general relativity and dark energy density, and it produces a clear dividing line in the universe between structures that will survive the expansion and those that will eventually be carried apart beyond any possibility of reunion. Our local group sits comfortably on the right side of that line. The 50 or more galaxies that make up our gravitationally bound collection, including the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies orbiting the two main spirals, are locked together by mutual gravity in a way that dark energy cannot undo. In approximately 4.5 billion years, as we have already noted, the Milky Way and Andromeda will begin their slow, majestic merger. Over hundreds of millions of years following that first encounter, they will pass through each other, separate partially, fall back together again, and ultimately coalesce into a single larger elliptical galaxy. The dwarf galaxies orbiting both will be incorporated or redistributed into the new structure. The result will be a single massive galaxy, the product of two spiral systems that have danced together across billions of years of cosmic history, and it will remain intact and gravitationally coherent for trillions of years to come. Beyond our local group, the nearest large structure is the Virgo cluster, a dense concentration of more than 1,000 galaxies approximately 65 million light-years away. The Virgo cluster is the gravitational heart of the larger Virgo supercluster, of which our local group is a peripheral member. Whether the Virgo cluster itself is bound to our local group, whether we will eventually fall into it and merge with it, or whether dark energy will push us apart faster than gravity can pull us together, is a question that depends on precise measurements of both the expansion rate and the masses involved. Current evidence suggests we're not strongly bound to the Virgo cluster. Dark energy is winning that particular tug of war. The Virgo cluster will likely recede beyond our event horizon in the far future, joining the long list of structures that are present in our sky today, and absent from it in the deep future. But within our local group, and potentially including a handful of the nearest galaxy clusters in our broader supercluster neighbourhood, we have a reachable cosmos, and that reachable cosmos, properly appreciated, is staggering in its own right. The Andromeda Galaxy alone contains approximately 1 trillion stars. The Triangulum Galaxy, the third largest member of our local group, visible to the naked eye under excellent conditions as a faint smudge in the constellation Triangulum, contains around 40 billion. The dwarf galaxies that orbit the Milky Way, including the large and small Magellanic Clouds, contain hundreds of millions of stars each. The total stellar inventory of the local group runs into the trillions. If humanity or its descendants were ever to master interstellar travel, the local group represents a territory of exploration so vast that billions of years of discovery would barely scratch its surface. There is something almost poignant about this when you hold it alongside everything the expansion is taking away. The universe is enormous, incomprehensibly, devastatingly enormous. It contains 2 trillion galaxies, each with hundreds of billions of stars spread across a volume nearly 93 billion light-years across. And of that total, our gravitational prison, our permanently accessible neighbourhood, is a tiny cluster of 50 galaxies in one small region of one unremarkable supercluster. The ratio of what we can reach to what exists is so small as to be effectively zero, and yet the territory we can reach, measured in human terms, is so boundless that the distinction between our accessible slice and the inaccessible remainder is almost philosophical rather than practical. We will never explore even the reachable portion in any meaningful completeness. The stars we can theoretically visit are already more than we could count in 1,000 lifetimes. And here is the thing that I find most striking about this asymmetry. Andromeda is coming toward us. While every other major galaxy in the universe flees, carried away by dark energy at speeds that increase with distance, Andromeda is approaching. It has been approaching for billions of years. Its gravity and ours are stronger than the expansion between us. And so rather than being carried apart, we're falling together in a slow, inevitable embrace, in a universe defined by separation, a universe whose dominant story is one of increasing isolation, of galaxies vanishing beyond horizons, of the great silence growing between everything. Andromeda is moving closer. It is the exception that makes the rule more vivid. It is the universe demonstrating, on one small and intimate scale, that connection is possible, that gravity, in the right circumstances and at the right distances, wins, that not everything is being taken away. Some things are arriving. Think about what it means to be truly alone. Not the ordinary loneliness of a quiet evening or an empty room, but the deep structural loneliness of existing in a place where no signal, no voice, no light from anything outside your immediate world can ever reach you. Where the darkness beyond your boundary is not just empty, but permanently, cosmically sealed. Where you could send a message in every direction simultaneously for billions of years and receive nothing back. Not because nobody is out there, but because the universe has placed everything else so far beyond your horizon that communication has become physically impossible. This is not a description of a nightmare or a thought experiment. It is a description of the long-term fate of every galaxy cluster in the universe, including, eventually, our own. The universe is not just expanding, it is isolating. And the isolation it is engineering, one receding galaxy at a time, is the loneliest condition that physics can produce. We have already established that galaxy clusters, gravitationally bound collections of galaxies like our local group, will remain intact as the universe expands. Gravity wins within those structures, holding them together against the outward pressure of dark energy. But between those clusters, dark energy wins completely. The spaces between clusters grow. They stretch. They become voids of increasing depth and width, filled with nothing but the thin intergalactic plasma and the background radiation of a cooling cosmos. And over time, as the expansion accelerates, those voids grow faster and faster, carrying galaxy clusters away from each other at speeds that no signal can match. Each cluster becomes an island, not separated from others by mere distance, the way cities on different continents are separated, but by an expanding gulf that actively prevents any form of connection. The isolation is not passive, it is enforced by the structure of the universe itself. Consider 2 galaxy clusters that are, today, 1 billion light-years apart. They can see each other, in the sense that ancient light from each has reached the other. They know of each other's existence through the messages that travelled across that billion light-years in the universe's younger, slower expanding past. But those messages are old. Today, the space between them is growing. In 1 billion years, they will be further apart. In 10 billion years, much further still. At some point, the recession velocity between them will exceed the speed of light, and any new signals sent from one to the other will never arrive. The clusters will have lost contact not because they moved, but because space between them grew beyond any signal's ability to cross. And crucially, neither cluster will receive any announcement of this fact. There is no alarm, no final message, no closing ceremony. The connection simply ends, quietly and completely, as the last photon that could ever make the crossing arrives, and no subsequent photon can follow it. This process is already underway throughout the universe. Right now, galaxy clusters that were once in causal contact with each other, able in principle to exchange signals across the distances between them, are crossing into permanent isolation from one another. The universe is partitioning itself. It is dividing its contents into sealed compartments, each one a gravitationally bound island surrounded by an expanding void that grows more uncrossable with every passing moment. The number of these islands is enormous. There are millions of galaxy clusters in the observable universe alone. Each one is becoming its own universe, in the functional sense of the word. Each one will eventually exist in a space so thoroughly emptied of external influence that nothing from outside can ever reach it again. Every cluster is becoming the only thing in its own sky. There is a concept in information theory called causal disconnection, the state in which two systems can no longer influence each other because no signal can travel between them. Causal disconnection is the deepest form of separation that physics recognizes. Two objects that are merely far apart can still, in principle, be connected by a sufficiently patient signal, but two objects that are causally disconnected are separated in a way that is absolute and permanent. Nothing that happens in one can ever affect the other. They might as well exist in separate universes, because from the perspective of physics and information they do. The accelerating expansion of the universe is a causal disconnection engine. It is systematically severing the causal connections between galaxy clusters, one by one, at a rate that increases over time, producing a universe that is becoming not just physically larger, but informationally fragmented, broken into isolated pieces that will never communicate again. Now imagine you are an intelligent being living inside one of those isolated clusters, billions of years from now. You look out from your galaxy into the darkness. You see your own cluster's stars, your own merged and reorganized galactic structure, the product of billions of years of internal evolution. But beyond your cluster there is nothing. No distant galaxy glowing faintly at the edge of visibility. No smudge of light from a neighboring supercluster. No cosmic microwave background radiation carrying the fingerprint of the Big Bang because it has redshifted to wavelengths too long to detect. Just darkness in every direction, complete and total, as far as any instrument can see. You might be forgiven for concluding that your cluster is the entirety of the universe, that there is nothing else, that there has never been anything else, that the cosmos is small and contained and fully mapped. You would be wrong, but you would have no way of knowing it. This is the loneliness I am describing. Not the loneliness of an individual or a civilization, but the loneliness of an entire gravitational island, a structure containing trillions of stars and potentially billions of inhabited worlds, cut off from the rest of reality by an expansion it cannot stop and cannot cross. The rest of the universe continues to exist, continues to evolve, continues to burn with the light of uncountable stars, but none of that light will ever reach the isolated cluster. None of that information will ever cross the void. The universe will be full of life and fire and complexity, distributed across millions of sealed compartments, each one invisible and unreachable to all the others, and each one, in its own expanding silence, utterly, cosmically, and permanently alone. This is where the expansion leads, not to emptiness, but to isolation, not to nothing, but to an infinity of somethings that will never know each other exist. Every star you have ever seen, every star that has ever been named or catalogued or pointed at by a human hand in wonder, is a temporary thing. A furnace burning through a finite fuel supply, brilliant and generous with its light for millions or billions of years, and then inevitably dark. The sun you depend on for every warm day and every photon of energy that has ever sustained life on this planet has been burning for approximately 4.6 billion years, and it has roughly another 5 billion years of hydrogen fuel remaining before it swells into a red giant and eventually collapses into a cold, dense remnant called a white dwarf. 5 billion years is a long time in human terms, long enough that the number loses its meaning if you try to hold it too literally. But in the context of the full lifespan of the universe, 5 billion years is not the end of the story. It is barely the middle of the second chapter. The universe has a future that stretches incomprehensibly beyond the death of our sun. and that future grows progressively, irrevocably darker. Cosmologists who study the long-term fate of the universe have divided its future history into a series of eras, each one defined by the dominant physical processes occurring at that time. We currently live in what is called the stelliferous era, the age of stars. It began shortly after the Big Bang, when the first stars ignited from clouds of primordial hydrogen and helium, and it will last for approximately 100 trillion years from now. 100 trillion. The current age of the universe is 13.8 billion years, which means the stelliferous era has barely begun. We are, cosmologically speaking, in the early morning of the age of stars. But even this vast era has an end, and it ends not with any single catastrophic event, but with the slow, quiet exhaustion of the raw material that stars require. As the universe ages, the gas and dust needed to form new stars becomes depleted, consumed by existing stellar generations or locked away in the remnants they leave behind. Star formation slows, new stars become rarer, and eventually, after 100 trillion years, the last star will form, burn for its allotted span, and go dark. After the stelliferous era ends, the universe enters what cosmologists call the degenerate era, a time dominated not by burning stars but by their cold remnants. White dwarfs, neutron stars, and brown dwarfs, objects that never ignited fully or that burned out long ago, will make up the bulk of the universe's visible matter during this period. White dwarfs cool slowly over incomprehensible timescales, radiating away the last of their thermal energy across trillions upon trillions of years. The universe during this era is not completely dark. The fading glow of cooling white dwarfs provides a dim, reddish illumination across the cosmos, but it is profoundly dimmer than anything we would recognize. The brilliant blues and whites and yellows of active stars are gone. The nebulae that stain the night sky with color have long since dissipated. The universe is settling into a deep, cold twilight, and the twilight is lengthening into what will eventually become permanent night. Then comes the black hole era. Current physics predicts that protons, the fundamental particles that make up the nuclei of all atoms, are not perfectly stable. They decay over timescales so vast that the number of years required to express the half-life of a proton makes the age of the universe look like a rounding error. If proton decay occurs, then over a timescale of roughly 10 to the power of 40 years, all ordinary matter, every planet, every asteroid, every white dwarf, every neutron star will dissolve. The atoms themselves will fall apart, releasing their constituent energy in a final slow evaporation of everything that was ever solid or tangible in the universe. By the time this process is complete, the only significant structures remaining will be black holes, vast, silent gravitational monuments to the matter that once orbited and burned and lived. Black holes do not decay through proton decay. They decay through a different process, one predicted by Stephen Hawking in 1974, called Hawking radiation. Hawking radiation is a quantum mechanical effect by which black holes slowly emit energy and lose mass over time. The smaller the black hole, the faster it evaporates. For stellar mass black holes, the evaporation timescale is approximately 10 to the power of 67 years. For the supermassive black holes at the centers of galaxies, objects containing millions or billions of solar masses, the evaporation time stretches to approximately 10 to the power of 100 years. These are numbers that have no analogy in human experience. They are not just large, they are large in a way that mocks every other large number we have encountered in this conversation. The age of the universe is 13.8 billion years. 10 to the power of 100 years is a 1 followed by 100 zeros, and yet eventually even the supermassive black holes will finish evaporating. One by one, they will release their last burst of Hawking radiation, and the universe will be left with nothing but the faintest traces of particles and photons spreading through an infinite, cold, dark, expanding void. This final state has a name. It is called heat death, or the Big Freeze, a condition in which the universe has reached maximum entropy, in which all energy has been distributed as evenly as possible across all of space, in which no temperature differences exist anywhere to drive any physical process, no gradients remain to power any reaction, no structure persists to host any complexity. It is not death in any dramatic sense. There is no explosion, no collapse, no final spectacular event. It is simply the last quiet exhalation of a universe that has been exhaling for an incomprehensible duration until there is nothing left to exhale. Thermodynamic equilibrium. Perfect, absolute, and eternal stillness. Lying in the dark right now, in this present moment that is so early in the universe's total lifespan that it barely registers on the full timeline, consider what this arc means. We exist in the brightest, most energetic, most structurally complex moment the universe will ever have. The stars are burning, new ones are still being born, galaxies are colliding and merging and creating the conditions for planets and chemistry and life. The cosmos is, right now, at the peak of its generative power, noisy, luminous, restless with activity, and all of it is temporary. Every photon of starlight is borrowed against a future of darkness. Every galaxy is a temporary arrangement of matter that will eventually dissolve back into the void. The farthest star will not just stay out of reach. One day, in a future so remote it has no human name, it will go out entirely. And the darkness that follows will be final, and permanent, and absolute. We are watching the universe spend itself, slowly and magnificently, in the only moment it will ever be this bright. There is a question that has been sitting quietly beneath everything we have explored tonight, and I want to bring it into the open now. If the farthest star will always stay out of reach, if the universe is sealed against our ambitions by its own accelerating expansion, if the horizon is shrinking and the darkness is coming, and the isolation is written into the mathematics of space-time itself, then what exactly are we supposed to do with that knowledge? What does it mean for how we live, for how we think about our place in the cosmos, for how we spend the brief and improbable span of years each of us is given on this small, warm, unlikely planet? Is this knowledge simply terrifying, a burden without a corresponding gift? Or is there something in the unreachability itself, something in the very fact of the limit, that contains a kind of meaning we would not have access to if the universe were otherwise? I want to suggest that unreachability is not a failure, not a deficiency in the universe or in us. It is not a problem waiting for a sufficiently advanced technology to solve. It is a feature, a structural property of the cosmos that, once genuinely understood and accepted, changes the texture of every moment you spend inside it. Because here is what the unreachable does when you let yourself feel it honestly. It makes the reachable precious. Every star that is within the gravitational embrace of our local group, every planet that orbits those stars, every moon that turns around those planets, becomes irreplaceable in a way it would not be if the universe were freely traversable in all directions. Scarcity creates value, limits create meaning, and the limit the universe has placed around us, while cosmically enormous, is still a limit, and limits are the precondition of any significance at all. Think about what it means to know that Andromeda is coming. In a universe defined overwhelmingly by separation and recession, the fact that one major galaxy is falling toward us, that gravity is winning that particular contest against expansion, carries a weight it would not carry in a universe where everything was equally accessible. Andromeda is not just a galaxy. It is the exception to the cosmic rule of isolation. It is the universe demonstrating, in the one case out of millions that applies to us most intimately, that connection is not only possible but inevitable. 4.5 billion years from now, the Milky Way and Andromeda will begin their merger. Stars from two separate galaxies, which spent billions of years separated by 2.5 million light-years, will be shuffled together into a single structure. That merger is a form of reaching. It is the universe reaching across a vast distance, through gravity rather than technology, and closing a gap that dark energy could not prevent. There is something almost tender about it, when you hold it against the backdrop of everything else flying apart. Here is the thing most people do not realize about living at the edge of understanding. The fact that we know the farthest star is unreachable, the fact that we have the mathematics and the cosmology and the observations to establish that fact with confidence, is itself one of the most remarkable things about our existence. We are not simply creatures who look up and feel wonder. We are creatures who have decoded the rules of the universe well enough to know where the rules lead, well enough to trace their implications across billions of years and across distances that no human will ever physically cross. We have never left this solar system in any meaningful sense. We have sent a handful of small probes into the outer reaches of our star's influence, and one of them has barely crossed into interstellar space. And yet, from that tiny provincial vantage point, we have deduced the existence of dark energy, mapped the cosmic web, detected the accelerating expansion, and calculated the long-term fate of a universe that will outlast us by a duration that makes our entire existence look like a mathematical rounding error. This is not a small thing. This is in fact extraordinary beyond any ordinary measure. The unreachable matters because reaching for it, mentally, conceptually, scientifically, is what made us who we are. Every advance in our understanding of the cosmos has come from the refusal to accept ignorance as a final answer. Every telescope built, every equation solved, every satellite launched, every data set analysed has been a form of reaching, not physically across the void, but intellectually across the boundary of what was previously unknown. The expansion of human knowledge is its own kind of expansion, driven by its own kind of energy, accelerating in its own right across the centuries. And unlike the cosmic expansion that separates us from the farthest stars, the expansion of understanding does not isolate, it connects. Every discovery about the nature of the universe is shared, built upon, refined, passed forward, a form of light that travels not through empty space but through minds and generations and time. There is also something important in the acceptance of limits that has nothing to do with science and everything to do with how a life feels from the inside. We live in a culture that treats limitation as a problem to be solved, distance as an obstacle to be overcome, every horizon as a temporary inconvenience pending sufficient ambition and technology. And in many domains, that attitude has served us extraordinarily well, but the universe at its larger scales does not yield to that attitude. The farthest star will stay out of reach regardless of how hard we try, regardless of how clever we become, regardless of what technologies future civilizations develop. The expansion does not care, the mathematics does not negotiate, and there is a kind of peace, a genuine, deep, non-trivial peace, that becomes available when you stop trying to argue with the structure of reality and simply inhabit it instead, not passively, not without curiosity or ambition, but with the settled awareness that the universe is what it is, that its limits are part of its nature, and that living within those limits is not a defeat, but simply the condition of existing inside this particular cosmos. The farthest star is unreachable, the horizon is shrinking, the darkness is coming slowly and over a time frame that dwarfs everything we are and everything we will ever build. And tonight, lying in the dark with all of that knowledge present and undenied, you are also here, warm, alive, aware, in possession of a mind capable of holding the entire arc of cosmic history from the Big Bang to the heat death, and finding it beautiful rather than merely cold. That combination, the vastness of what cannot be reached, and the smallness and warmth of the thing doing the reaching, is not a tragedy. It is the specific and unrepeatable shape of being a conscious creature in this universe. It is what you are. And it is, I want to suggest, quite enough. We have travelled a long way tonight, from the familiar act of looking up at a dark sky, through the nature of light and the scale of our galaxy, out through the cosmic web and the observable horizon, into the mechanics of dark energy and accelerating expansion, through the thought experiment of an impossible journey, past the fate of isolated galaxy clusters and the long extinction of stars, and finally into the question of what all of it means for the small, warm, improbable things we are. It has been a journey not through space. We have not moved an inch from wherever you're lying or sitting right now, but through understanding. And understanding, as I hope tonight has shown, is its own kind of travel. It takes you places that no spacecraft can reach. It crosses distances that no engine can cover. It arrives, quietly and without fanfare, at truths that are more vertiginous and more beautiful than any physical destination could ever be. Here is the truth that I keep returning to, the one that anchors everything else we have discussed tonight. The universe is approximately 13.8 billion years old. For the first several hundred million years of its existence, there were no stars, no planets, no chemistry beyond the simplest atoms, hydrogen, helium, traces of lithium, drifting in an expanding, cooling darkness. Then the first stars ignited, burned bright and fast and died, seeding space with heavier elements forged in their cores. Generations of stars followed, each one enriching the cosmos with more complex chemistry. Eventually, around some of those stars, planets formed. On at least one of those planets, and almost certainly on many more we have not yet confirmed, chemistry became biology. Biology became complexity. Complexity became, after billions of years of patient evolution, something capable of asking where it came from and what surrounds it, something capable of building telescopes and writing equations and lying in the dark at night thinking about the edge of the observable universe. The universe made you, and through you, it made something it had never had before, a way of knowing itself. This is not a metaphor. It is a physical fact with profound implications. The atoms in your body were forged in the cores of stars that died before the sun existed. The carbon in your cells, the oxygen in your lungs, the iron in your blood, these elements did not exist in the early universe. They were created by nuclear fusion in stellar interiors over billions of years, scattered into space by stellar winds and supernova explosions, gathered into new solar systems, incorporated into planets, assembled by chemistry and biology over geological timescales, into the improbable architecture of a living, thinking creature. You are not separate from the universe looking at it from outside. You are the universe, locally organized into a form that can look at itself. When you contemplate the farthest star, the universe is contemplating its own edge. When you feel awe at the scale of the cosmos is feeling awe at itself. This is what you are. This is what we all are. And it is, by any honest measure, the most astonishing thing the universe has ever produced. And what has this particular piece of the universe, this temporary, fragile, luminous arrangement of stardust that is you, tonight, in the dark, what has it learned? It has learned that the cosmos is almost incomprehensibly vast, and that it is expanding, and that the expansion is accelerating, and that the farthest star will always stay out of reach. It has learned that most of the universe is made of things we cannot see and do not understand. It has learned that the night sky is a time machine, that every point of light is a message from the past, that some of those messages come from objects that no longer exist. It has learned that the universe began in an unimaginable heat, and will end in an unimaginable cold, and that in between, in this brief extraordinary window of stellar warmth and complexity, life and mind and wonder became possible. You have learned all of this tonight. The universe has learned all of this about itself through you. That is not nothing. That is everything. I want you to think about the farthest star one more time, not with sadness, not with the weight of its unreachability, but with something closer to reverence. That star, whatever it is, wherever it burns in the ancient light we receive from the edge of the observable universe, has been there for billions of years, fusing hydrogen into helium in the dark, unaware of anything beyond its own nuclear fire. It does not know it exists. It does not know it is beautiful or ancient or impossibly far away. It does not know that on a small planet orbiting a modest star in a peripheral galaxy, a creature made of its own cast-off elements once looked up and found it and felt something vast and nameless in its chest. The star does not know any of this, but you do. You carry the knowledge of that star's existence inside you, along with the knowledge of its distance and its age and the dark energy that prevents you from ever reaching it. You are the place where the universe stores its self-awareness, and that self-awareness, fragile, temporary, miraculous, is worth more than the ability to cross any distance. The farthest star will always stay out of reach. The horizon will continue to shrink, galaxies will continue to recede, the darkness will continue to deepen, on timescales so vast they dissolve all ordinary meaning. None of that changes tonight. None of that is resolved or softened by anything we have discovered together in the last few hours. The universe is what it is, enormous and expanding and ultimately cooling towards silence, and no amount of wonder changes the physics. But wonder is not a response to physics. Wonder is what happens when a conscious mind meets the true scale of things and does not look away. And you did not look away tonight. You stayed with it. You followed the light all the way to the edge, and you sat with the silence beyond it, and you let the full weight of the cosmos settle on you without flinching. That matters. It matters more than I can adequately say. We are the universe noticing itself. We are 13.8 billion years of cosmic evolution, briefly concentrated into a form that can feel awe, ask questions, and find meaning in the dark. The farthest star is out of reach, and the night is vast, and the silence between galaxies is growing. And here, in the middle of all of that immensity, you are warm and alive and aware, and the universe is aware through you, and for this one improbable moment, that is more than enough. Thank you for joining me on this journey tonight. If this exploration moved something in you, please consider leaving a like or subscribing. It is a small gesture, but it helps more curious minds find their way to these questions. The next time you step outside and look up at the night sky, remember what you now know. Remember that the light reaching your eyes is ancient and has travelled unimaginable distances to find you. Remember that you are made of the same fire as the stars you're looking at. Remember that the universe, in its 13.8 billion years of existence, has managed to produce exactly this, a creature capable of looking up and understanding, even a little, what it is looking at. Sleep well tonight, and keep looking up at the stars. Good night.